Welcome back to The Explainer. I am absolutely thrilled you're here today because, honestly, we're going to explore a completely revolutionary intersection of computer science, advanced mathematics, and intellectual property law. We're diving into episode 43, looking at the protective shell. Today we're unpacking a fascinating bridge between deterministic digital states, the absolute crisis of corporate IP hoarding, and a brilliantly unexpected solution inspired by, of all things, the music industry. So, let's just get right into it.
Okay, I want to kick things off with a number that should absolutely shock you. 250,000. Just let that sink in for a second. That staggering figure actually represents the estimated number of active, overlapping patents covering a single modern smartphone. That is 250,000 individual legal protections touching literally everything from the antenna all the way down to the screen. It perfectly sets up just how hostile the modern technology landscape has become.
You know, economists actually have a specific name for this corporate capture crisis. UC Berkeley economist Carl Shapiro defined it back in 2001 as a patent thicket, and it's exactly what it sounds like. It's a dense web of overlapping IP rights that a company literally has to hack its way through just to commercialize new tech. Think about it. You might have this viable, incredible invention, you've got the funding, you've got a market ready for it, but standing right in your way is this impenetrable tangle of legal rights. It's not a competitive moat anymore, it's a legal minefield. And it completely stifles independent research and blocks these viable inventions from ever reaching us, the consumers. Why? Because massive companies just use these thickets as defensive shields, or worse, offensive weapons to absolutely crush competitors and drain their resources in court.
So how do we fix this whole mess? Well, here is our roadmap for today's explainer. We're hitting the corporate capture crisis, merging data and logic, the math of non-halting systems, the protective shell, and finally, a music royalty model. We're going to systematically unpack how one specific invention, patent WO 2020-16021, solves this chaos.
All right, let's jump straight into Pillar 1, merging data and logic, which is really the architectural breakthrough of this whole system.
To really grasp this breakthrough, we first have to recognize that traditional enterprise software is fundamentally divided. It's split into two. You have your static database sitting over here on one side and your active computing logic over on the other. And this divide, it causes massive operational headaches, namespace collisions, database logic mismatches, the whole shebang. It's like classical linguistics. Under the old paradigm, databases are basically just nouns. They just sit there and hold static data. Meanwhile, your general-purpose software acts as the verbs. It's the active execution logic doing the work. But the inventor, Kyle Smith, created a unified system using the hierarchical script database, which is also known as CTreeDB. By leveraging a JSON-like tree structure, it perfectly merges inactive data and executable function objects into single, unified nodes. To use Smith's own linguistic analogy, it's like taking those separated nouns and verbs and finally putting them right next to each other to form actual working sentences and paragraphs within the application runtime. It's a total game changer.
Now, right at the absolute core of this new logical structure is what's called the synkernel function, and that stands for thesis, antithesis, synthesis. I want you to think of this as a super strict logical bouncer at the door of your database. Step 1. The bouncer checks if a space in the database is empty. Step 2. If it is empty, great. It synthesizes the new data directly into that slot. But step 3. If data already exists in that spot, the bouncer violently rejects the input. No entry. This prevents accidental overwrites unless, and this is key, a developer explicitly uses overwrite option flags. It's kind of like a VIP pass. You can use an O flag to bypass the empty cell requirement or an N flag to just force an overwrite. Because the data is perfectly parsed and validated against a very strict schema before a single byte is ever executed, it completely eliminates those chaotic scope issues we constantly see in traditional event-driven programming.
Moving right along to Pillar 2, the math of non-halting systems. This is all about achieving continuous digital flow.
And this brings us to the multi-million-dollar question, right? How do we actually prevent these recursive systems from crashing, or what computer scientists call halting? I mean, when your database is acting as a self-reproducing automaton, literally spawning new logical nodes with every single event, how on earth do you stop it from just blowing up and resulting in a fatal stack overflow?
Well, the mathematical answer Smith devised for this is absolutely brilliant. It's called Pythagorean scaling. It uses Pythagorean triples, like the classic 3-4-5 triangle from high school geometry, where A is 3, B is 4, and C is 5. The system applies a scale symmetry log function, specifically C minus B over A to the power of n. So in our 3-4-5 example, that resolves to a scale parameter of exactly 1/3. By treating geometric forms as continuous data streams, this creates an infinite progression of self-similar tilings. Because it relies on these infinite, non-repeating geometric sequences, the cellular automata literally never reach a terminal state. It completely dodges Stack Overflow by treating state changes as continuous geometric transitions instead of halting computations.
Okay, I know that was a bit dense, so let's visualize the math to make this super clear. Picture this in your head. Imagine a 12 by 18 parent rectangle. Inside of it, there's a repeating 12 by 10 inner rectangle. Now, using that scale symmetry function we just talked about, these rectangles scale down infinitely along a central symmetry line. It's like an endlessly zooming animation, just zooming in forever. This is such a vital visual anchor. Instead of treating data as static, halted, or isolated points, the database is actually modeling its state history as a continuous geometric wave. It allows recursive calculations to run safely, indefinitely. Imagine having applications that literally never freeze or require rebooting just to clear their memory. That is the real power of this geometric math in action.
Okay, tying this all back to our main theme, let's hit Pillar 3, the protective shell, legal engineering, and corporate defense.
So, we have our architectural breakthrough, we have our infinite mathematical engine, but how does this connect back to our opening problem? Remember that devastating patent thicket? Well, the absolutely crucial point is this contrast here. Standard patents are, traditionally, monopolistic weapons. They are those dense thickets weaponized by large corporations or patent trolls, basically to extract licensing fees and just crush smaller competitors. But the seed tree DB patent, WO 2020-160-0021, takes a radically different approach. Rather than acting as this rigid commercial monopoly, Smith uses his background in IP law to legally engineer the patent as a protective shell. It acts almost like a good shepherd, legally anchoring the architecture and shielding the open-source codebase from corporate lock-in, or, being secretly ingested by closed-source AI systems without permission. It turns the weapon into a shield.
And finally, we arrive at Section 4, a music royalty model. Let's talk about reimagining open-source economics.
This is where it gets super interesting, because the inventor actually comes from a background in music publishing and royalty collection. SeedTreeDB builds on an economic model that we already know works beautifully. In the music industry, performing rights organizations, or PROs, figured out this brilliant balance years ago. Radio airplay remains completely free for public listeners, right? You turn on the radio, you hear a song. But the actual songwriters still get compensated through back-end royalty pools. Smith applies this exact same model to open-source software. Through the patent's protective shell, the open-source code stays completely free for everyday developers to inspect, modify, and use to their heart's content. But, and this is the kicker, if a massive corporation deploys that software into a high-volume commercial revenue engine, the legally engineered patent kicks in and mandates that royalties are paid back to the original authors.
Let's look at the breakdown here to really cement this paradigm shift. Under traditional proprietary licensing, you've got high costs, captive authors, and completely closed code protected by trade secrets. Now, standard open source fixes the cost issue, but it leaves authors totally struggling to monetize, relying on pretty weak copyright disclaimers. SeedTreeDB's legally engineered model is the ultimate bridge between the two. You get zero cost for standard users, but a fully enforced utility patent ensures that massive corporations actually have to pay royalties for commercial deployment. It solves the biggest problem in open source today.
I want to end today's explainer with this memorable code-like quote from the inventor himself defining his ultimate goal. It reads, "Author, opt in for revenue. Consumer, zero cost." It perfectly synthesizes everything we've looked at today. Think about it. If invention is supposed to be a truly collaborative, deeply social ecosystem, shouldn't our legal and economic structures actually reward the creators instead of the corporate hoarders? Imagine a world where open-source software authors are respected and compensated exactly like hit songwriters, while the digital commons remains entirely free for the rest of us to learn from and build upon. It's a totally reimagined digital economy. So what do you think? Are we ready for a system that actually pays the creators? Thanks so much for joining me on this explainer, and I'll see you on the next one.